Hello, I'm Jonathan Aldrich, and today let's talk about object lifetimes and storage management. The lifetime of an object, such as a variable, is from when the space is allocated for that variable until when it's reclaimed. The lifetime of a binding, which might include the variable's name, for example, starts from when it is associated with that object or entity to when the association ends. Now, what happens if these lifetimes are different? If the lifetime of a binding is different from the lifetime of the entity being bound? Well, if the binding outlives the entity, then we have a dangling reference. For example, in the code below, an object is passed that's on the heap is passed by reference in C++, and it's deallocated before the function returns. We have a dangling reference, and this could cause an error or security vulnerability in the code. On the other hand, if an entity outlives the last binding to it, then that entity is garbage. For example, in functional programming languages, a data structure may be bound to many different names, and it may not be clear when the last name goes out of scope. In these situations, garbage collection is used to reclaim the space that has been used by garbage. We say that a binding is active whenever it can be used in the program. Bindings can be temporarily deactivated and then activated later again. For example, if one variable is shadowed by another that has the same name. Also, if we call another function, while that function executes, the bindings from the first function may not be available. Finally, for static variables inside a function, when the containing function is not running, then that variable is not actively, the binding for that variable is not actively usable. Let's look at an example of shadowing. What does this C code print? Take a look at it for a moment. Pause the video if you'd like to think about it. In this code, we have an outer x binding to 5, and then an if statement, and then an inner binding of x to 7. This inner statement shadows the x equals 5 binding from outside the if statement. And so the print x inside the if statement will print 7 rather than 5. We say that the inner binding shadows the outer one. Let's look at the timeline of an entity such as a variable. We start with the creation of entities, that is, the allocation of space for them. Generally, if it's a local variable or a parameter, this will happen at function entry. But it could also happen at an allocation statement time. Later, we create a binding to that variable, and this typically happens at the variable declaration, which for parameters is at the beginning of the function, but for other variables might be in the middle of the function. We then can use the variables via their bindings. We might temporarily deactivate or shadow those bindings so they can't be used, perhaps if we call another function. But then we can reactivate the bindings when that function returns. At the end of the scope, we will destroy the binding, and then we destroy the entity itself, perhaps at the end of the scope, or the end of a function body, or perhaps at a free statement if we're allocating on the heap. Thus, we can talk about the lifetimes of objects and the management of storage that refers to them. We have three primary storage allocation mechanisms used in programs. Static allocation allocates an object to a fixed location in program memory. This is good for objects that live for the entire length of the program. Stack allocation follows the call and return of the functions and is good for objects that live just as long as the function does. Whereas a heap allocation is allocated at runtime in a way that's independent of the call structure of the program. So let's talk about static allocation first. Again, this is for entities that live for the entire program execution. Things like the code of the program, global variables, any static variables and functions, any explicit constants such as strings, sets, variables that have a constant and immutable value, and finally, scalars may be stored in instructions. On the other hand, we use stack allocation for entities that live just for the length of a function invocation. Typically, this includes parameters, local variables, and temporaries. Why would we use a stack? Well, for one thing, if we have a recursive routine, then there may be several instances of a function on the call stack at the same time, and we need to have different space for those. And so using a stack allocates space for variables each time the function is called. Furthermore, we can reuse space, and this happens in all programming languages, whereas there are some programming languages where we don't need space for recursive routines because there's no recursion. That's getting pretty rare, but Fortran and also some domain-specific languages may not have recursion support. But in all programming languages, we can reuse space. Essentially, the stack allows us to use only the space for the variables that are in scope in the functions that are currently executing. An illustration of a stack is shown here, where we start with A, B, and then several recursive calls to C, and then we call C, D, and E, and then return back to A. Why might we not use a stack? Well, even for things like local variables, in functional languages, local variables might be referenced after the function returns due to closures, which we'll talk about later in this chapter. So local variables might be allocated on the heap in these functional languages. Let's zoom in and look at stack allocation. So the stack of the program typically looks like this. We start with subroutine A, we allocate space for all the things it needs, and then when subroutine A calls subroutine B, we allocate space for subroutine B. We might do that again if subroutine B calls itself recursively, then we call subroutine C and subroutine D. I'm showing here the stack growing upwards because that's the common way to visualize a stack. It's like a stack of paper, you put things on top. But in practice, generally in implementations, the stack will grow from high addresses towards lower addresses. So that's something important to remember when to translate kind of the visualization of a stack to the way that it's implemented in typical languages. We have a stack pointer that keeps track of the top of the stack. That's where we might allocate new frames. And we have a frame pointer that refers to the current frame of the subroutine that we're in. In many modern implementations, the frame pointer no longer exists. We simply offset backwards from the stack pointer. Looking in detail at a routine, such as subroutine C in this case, the very last part of the allocation on the stack for that routine will be the return address. I guess that's the part that's closest to the previous function. And so that is where we will jump to when we return from the function. And conventionally, the frame pointer points to just above the return address. There might be some bookkeeping for the function. That depends on the particular implementations. Then we'll have local variables for subroutine C. We might have some temporary storage space, again allocated on the stack. And when we're about to call subroutine D, we will pass the arguments to subroutine D at the top of the stack space from subroutine C. So when subroutine D accesses its arguments, it'll actually go down the stack from the return address to find its arguments. The maintenance of the stack is typically the responsibility of a calling sequence of instructions in the calling function, and then the prologue and epilogue of the subroutine that is called. Typically, because most procedures have several callers, we can save space if we can do most of the work of the maintenance of the stack in the callee's prologue and the epilogue. But there may be trade-offs between space savings and time savings, depending on the details of the implementation. Sometimes variables live for longer, or perhaps not quite as long, as the functions that allocate them. For that, we can use heap-based allocation. This supports lifetimes that don't match the call stack. It requires explicit management, that is, allocation with malloc and free in many languages, or garbage collection in languages that have automatic storage management. Unfortunately, in heap allocation, we can have wasted space due to fragmentation, especially in explicitly managed situations where removing these fragmentations are hard. To illustrate fragmentation, let's look at the following animation. Here we're allocating one block at a time, but at some point we might free some variables. We allocate more blocks, we free some space, and we end up perhaps with something like this. Now, we have some space that is used, we have some space that's free, and now we might want to allocate a new block. That block might use less storage than we have available in the memory. But if the free space in the memory is broken up into several segments and none of them are big enough to hold the block, then we can't allocate them, even if there's enough space overall. In general, fragmentation can sometimes cause a surprising amount of space wastage. So it's an important consideration in memory management. And some garbage collection algorithms are specifically designed to combat fragmentation. Let's check our understanding.